CIET NCERT presents the audiobook Ganit Prakash, Textbook of Mathematics for Class 6.
Chapter number 5, Prime Time, page number 107. 5.1, Common Multiples and Common Factors. Idli Vada Game. Children, sit in a circle and play a game of numbers. One of the children starts by saying 1. The second player says 2 and so on. But when it is the turn of 3, 6, 9, etc., multiples of 3, the player should say idli instead of the number. When it is the turn of 5, 10, etc., multiples of 5, the player should say vada instead of the number. When a number is both a multiple of 3 and a multiple of 5, the player should say idli vada. If a player makes any mistake, they are out. The game continues in rounds till only one person remains. For which numbers should the player say idli instead of saying the number? These could be 3, 6, 9, 12. These would be. अच्छा सुनाई वैसे दिया हाँ तो यहीं से बोलो ना. These could be 3, 6. These would be बोल रही हूँ. Repeat. These would be 3, 6, 9, 12, 18, etc. and so on. For which numbers should the player say vada? These would be 5, 10, 20 and so on. Which is the first number for which the players should say idli vada? It is 15, which is a multiple of 3 and also a multiple of 5. Find out other such numbers that are multiples of both 3 and 5. These numbers are called dash. Page number 108. Figure it out. Question number 1. At what number is idli vada said for the 10th time? Question number 2. If the game is played for the numbers from 1 to 90, find out part A. How many times would the children say idli, including the times they say idli vada? Part B. How many times would the children say vada, including the times they say idli vada? Part C. How many times would the children say idli vada? Question number 3. What if the game was played till 900? How would your answers change? Question number 4. Is this figure somehow related to the idli vada game? Hint is, imagine playing the game till 30. Draw the figure if the game is played till 60. A picture is given in which two circles are intersecting. In one circle, multiples of 3 are written as 3, 9, 12, 21, 27, 15, 30, 18. And in the other circle, multiples of 5 are written as 10, 5, 25, 20, 15 and 30. The common multiples of 3 and 5 are represented in the common portion shared by both the circles. Let us now play the idli vada game with different pairs of numbers. Part A, 2 and 5. Part B, 3 and 7. Part C, 4 and 6. We will say idli for multiples of the smaller number vada, for multiples of the larger number, and idli vada for common multiples. Draw a figure similar to the figure 5.1 if the game is played up to 60. Here we have dialogues between two kids here. One saying, "Yesterday we played this game with two numbers. We ended up saying just idli or idli vada and nobody said just vada." The other kid says, "Oh, what could those numbers be?" The first kid replies, "One of the numbers was 4. Page number 109. Which of the following could be the other number? 2, 3, 5, 8 or 10? Jump jackpot. Jumpy and Grumpy play a game. Grumpy places a treasure on some number. For example, he may place it on 24. Jumpy chooses a jump size. If he chooses 4, then he has to jump only on multiples of 4 starting at 0. Jumpy gets the treasure if he lands on the number where Grumpy placed it. Which jump sizes will get Jumpy to land on 24? If he chooses 4, Jumpy lands on 4, then 8, then 12, then 16, then 24, then 28, and so on. Other successful jump sizes are 2, 3, 6, 8, and 12. Here we find a picture of a number line on which the numbers are represented from 0 to 24. Different jumps are represented with the help of different colors in this picture. What about this jump of sizes 1 and 24? Yes, they also will land on 24. The numbers 1, 2, 3, 4, 6, 8, 12, 24 all divide 24 exactly. Recall that such numbers are called factors or divisors of 24. Grumpy increases the level of the game. 2 treasures are kept on 2 different numbers. Jumpy has to choose a jump size and stick to it. Jumpy gets the treasures only if he lands on both the numbers with the chosen jump size. As before, Jumpy starts at 0. Grumpy has kept the treasures on 14 and 36, and Jumpy chooses a jump size of 7. Will Jumpy land on both the treasures? Starting from 0, he jumps to 7, then 14, then 21, then 28, then 35, and then 42, and so on. We see that he landed on 14 but did not land on 36. So he does not get the treasure. What jump size should he have chosen? Page number 110. The factors of 14 are 1, 2, 7, 14. So these jump sizes will land on 14. The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18 and 36. These jump sizes will land on 36. So, the jump sizes of 1 or 2 will land on both 14 and 36. Notice that 1 and 2 are the common factors of 14 and 36. The jump sizes using which both the treasures can be reached are the common factors of the two numbers where the treasures are placed. What jump size can reach both 15 and 30? There are multiple jump sizes possible. Try to find them all. Look at the table given here. What do you notice? We have a table representing numbers from 31 to 70, and some numbers are encircled. The numbers encircled are 32, 36, 40, 44, 48, 52, 56, 60, 64, and 68. And some numbers are shaded. The numbers which are shaded here are 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, and 69. In the table, question number 1, is there anything common among the shaded numbers? Question number 2, is there anything common among the circled numbers? Question number 3, which numbers are both shaded and circled? What are these numbers called? Figure it out. Question number 1. Find all multiples of 40 that lie between 310 and 410. Page number 111. Question number 2. Who am I? Part A. I am a number less than 40. One of my factors is 7. The sum of my digits is 8. Part B. I am a number less than 100. Two of my factors are 3 and 5. One of my digits is one more than the other. Question number 3. A number for which the sum of all its factors is equal to twice the number is called a perfect number. The number 28 is a perfect number. Its factors are 1, 2, 4, 7, 14, and 28. Their sum is 56, which is twice 28. Find a perfect number between 1 and 10. Question number 4. Find the common factors of Part A, 20 and 28. Part B, 35 and 50. Part C, 4, 8 and 12. Part D, 5, 15 and 25. Question number 5. Find any three numbers that are multiples of 25 but not multiples of 50. Question number 6. Anshu and his friends play the Idli Vada game with two numbers which are both smaller than 10. The first time anybody says Idli Vada is after the number 50. What could the two numbers be which are assigned Idli and Vada? Question number 7. In the treasure hunting game, Grumpy has kept treasures on 28 and 70. What jump sizes will land on both the numbers? Question number 8. In the diagram given, Guna has erased all the numbers except the common multiples. Find out what those numbers could be and fill in the missing numbers in the empty regions. Here we find a picture of two circles. One is red in color and the other is blue in color. The red circle has numbers 72, 48 and 24, which are also present in the circle which is blue in color. That means they are the common multiples of the numbers in red circle and blue circle. We are supposed to write the multiples of which number are given in red circle. There's a dash. And we are also supposed to mention multiples of which number are there in blue circle. Question number 9. Find the smallest number that is a multiple of all the numbers from 1 to 10 except for 7. Question number 10. Find the smallest number that is a multiple of all the numbers from 1 to 10. Page number 112. 5.2 Prime numbers. Guna and Anshu want to pack figs, that is anjeer, that grow in their farm. Guna wants to put 12 figs in each box and Anshu wants to put 7 figs in each box. How many arrangements are possible? Think and find out the different ways how Guna can arrange 12 figs in a rectangular manner. Also, Anshu can arrange 7 figs in a rectangular manner. Guna has listed out these possibilities. Observe the number of rows and columns in each of the arrangements. How are they related to 12? In the second arrangement, for example, 12 figs are arranged in 2 columns of 6 each, or 12 is equal to 2 into 6. Anshu could make only one arrangement, that is 7 into 1 or 1 into 7. There are no other rectangular arrangements possible. In each of the Guna's arrangements, multiplying the number of rows by the number of columns gives the number 12. So, the number of rows or columns are factors of 12. We saw that the number 12 can be arranged in a rectangle in more than one way, as 12 has more than 2 factors. The number 7 can be arranged in only one way, as it has only 2 factors, 1 and 7. Numbers that have only 2 factors are called prime numbers or primes. Here are the first few primes: 2, 3, 5, 7, 11, 13, 17, 19. Notice that the factors of a prime number are 1 and the number itself. What about numbers that have more than 2 factors? They are called composite numbers. The first few composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20. Here on this page we can find pictures showing how the squares are arranged in a pattern 1 by 12 and 6 by 2, that is 12, and also 4 by 3, that is equal to 12. One blue color pattern is also representing 1 by 7 arrangement. Page number 113. What about 1, which has only one factor? The number 1 is neither a prime nor a composite. How many prime numbers are there from 21 to 30? How many composite numbers are there from 21 to 30? Can we list all the prime numbers from 1 to 100? Here is an interesting way to find prime numbers. Just follow the steps given below and see what happens. We will take a grid of numbers from 1 to 100 and we will perform this activity. Step 1. Cross out 1 because it is neither prime nor composite. Step 2. Circle 2 and then cross out all multiples of 2 after that, that is 4, 6, 8 and so on. Step 3. You will find that the next uncrossed number is 3. Circle 3 and then cross out all the multiples of 3 after that. That is 6, 9, 12 and so on. Step 4. The next uncrossed number is 5. Circle 5 and then cross out all the multiples of 5 after that. That is 10, 15, 20 and so on. Step 5. Continue this process till all the numbers in the list are either circled or crossed out. All the circled numbers are prime numbers. All the crossed out numbers other than 1 are composite numbers. This method is called the sieve of Eratosthenes. This procedure can be carried on for numbers greater than 100 also. Eratosthenes was a Greek mathematician who lived around 2200 years ago and developed this method of listing primes. We can find a cartoon on this page in which a dialogue displayed is, "It is definitely not some magic. There should be a reason why it works." Page number 114. Guna and Anshu started wondering how this simple method is able to find prime numbers. Think how this method works. Read the steps given above again and see what happens after each step is carried out. Figure it out. Question number 1. We see that 2 is a prime and also an even number. Is there any other even prime? Question number 2. Look at the list of primes till 100. What is the smallest difference between two successive primes? What is the largest difference? Question number 3. Are there an equal number of primes occurring in every row in the table on the previous page? Which decades have the least number of primes? Which have the most number of primes? Primes through the ages. Prime numbers are the building blocks of all whole numbers. Starting from the time of the Greek civilization, more than 2000 years ago, to this day, mathematicians are still struggling to uncover their secrets. Food for thought. Is there a largest prime number, or does the list of prime numbers go on without an end? A mathematician named Euclid found the answer, and so will you in a later class. Fun fact: the largest prime number that anyone has written down is so large that it would take around 6,500 pages to write it. So, they could only write it on a computer. Question number 4. Which of the following numbers are primes? 23, 51, 37, 26. Question number 5. Write 3 pairs of prime numbers less than 20 whose sum is a multiple of 5. Question number 6. The numbers 13 and 31 are prime numbers. Both these numbers have same digits 1 and 3. Find such pairs of prime numbers up to 100. Question number 7. Find 7 consecutive composite numbers between 1 and 100. Question number 8. Twin primes are pairs of primes having a difference of 2. For example, 3 and 5 are twin primes. So are 17 and 19. Find the other twin primes between 1 and 100. Page number 115. Question number 9. Identify whether each statement is true or false. Explain. Part A. There is no prime number whose units digit is 4. Part B. A product of primes can also be prime. C. Prime numbers do not have any factors. D. All even numbers are composite numbers. E. 2 is a prime and so is the next number 3. For every other prime, the next number is composite. Question number 10. Which of the following numbers is the product of exactly 3 distinct prime numbers? 45, 60, 91, 105, 330. Question number 11. How many 3-digit prime numbers can you make using each of 2, 4 and 5 ones? Question number 12. Observe that 3 is a prime number and 2 into 3 plus 1 is equal to 7 is also a prime. Are there other primes for which doubling and adding 1 gives another prime? Find at least 5 such examples. 5.3 Co-prime numbers for safekeeping treasures. Which pairs are safe? Let us go back to the treasure finding game. This time, treasures are kept on 2 numbers. Jumpy gets the treasures only if he is able to reach both the numbers with the same jump size. There is also a new rule which says a jump size of 1 is not allowed. Where should Grumpy place the treasures so that Jumpy cannot reach both the treasures? Will placing the treasure on 12 and 26 work? No. If the jump size is chosen to be 2, then Jumpy will reach both 12 and 26. What about 4 and 9? Jumpy cannot reach both using any jump size other than 1. So, Grumpy knows that the pair 4 and 9 is safe. Check if these pairs are safe. A. 15 and 39. B. 4 and 15. C. 18 and 29. D. 20 and 55. Page number 116. What is special about safe pairs? They don't have any common factor other than 1. 2 numbers are said to be co-prime to each other if they have no common factor other than 1. Example, as 15 and 39 have 3 as a common factor, they are not co-prime, but 4 and 9 are co-prime. Which of the following pairs of numbers are co-prime? A. 18 and 35. B. 15 and 37. C. 30 and 415. D. 17 and 69. E. 81 and 18. While playing the Idli Vada game with different number pairs, Anshu observed something interesting. First, sometimes the first common multiple was the same as the product of the 2 numbers. Second, at other times the first common multiple was less than the product of the 2 numbers. Find examples for each of the above. How is it related to the number pair being co-prime? Co-prime art. Observe the following thread art. The first diagram has 12 pegs and the thread is tied to every 4th peg. We say that the thread gap is 4. The second diagram has 13 pegs and the thread gap is 3. What about the other diagrams? Observe these pictures, share and discuss your findings in class. The pictures of these thread diagrams are given here with the pegs at different positions. In some diagrams, the thread is tied to every peg. In some, it is not. Is it related to the 2 numbers, the number of pegs and the thread gap being co-prime? Page number 117. Make such pictures for the following. A. 15 pegs, thread gap of 10. B. 10 pegs with thread gap of 7. C. 14 pegs with thread gap of 6. D. 8 pegs with thread gap of 3. 5.4 Prime factorization. Checking if two numbers are co-prime. Teacher says, are 56 and 63 co-prime? Anshu and Guna. They reply, if they have a common factor other than 1, then they are not co-prime. Let us check. Anshu says, I can write 56 is equal to 14 into 4 and 63 is equal to 21 into 3. So, 14 and 4 are factors of 56. Further, 21 and 3 are factors of 63. So, there are no common factors. The numbers are co-prime. Guna says, hold on. I can also write 56 is equal to 7 into 8 and 63 is equal to 9 into 7. We see that 7 is a factor of both numbers. So, they are not co-prime. Clearly, Guna is right, as 7 is a common factor. But where did Anshu go wrong? Writing 56 is equal to 14 into 4 tells us that 14 and 4 are both factors of 56, but it does not tell all the factors of 56. The same holds for the factors of 63. Try another example. 80 and 63. There are many ways to factorize both numbers. 80 is equal to 40 into 2, that is equal to 20 into 4, that is equal to 10 into 8, that is equal to 16 into 5, that is equal to some more you can try. 63 is equal to 9 into 7, that is equal to 3 into 21, that is equal to, try out for yourself. We have written question mark to say that there may be more ways to factorize these numbers. But if we take any of the given factorizations, for example, 80 is equal to 16 into 5 and 63 is equal to 9 into 7, then there are no common factors. Can we conclude that 80 and 63 are co-prime? As Anshu's mistake above shows, we cannot conclude that, as there may be other ways to factorize the numbers. What this means is that we need a more systematic approach to check if two numbers are co-prime. Page number 118. Prime factorization. Take a number such as 56. It is composite, as we saw that it can be written as 56 is equal to 4 into 14. So, both 4 and 14 are factors of 56. Now, take one of these, say 14. It is also composite and can be written as 14 is equal to 2 into 7. Therefore, 56 is equal to 4 into 2 into 7. Now, 4 is composite and can be written as 4 is equal to 2 into 2. Therefore, 56 is equal to 2 into 2 into 2 into 7. All the factors appearing here, 2 and 7, are prime numbers. So, we cannot divide them further. In conclusion, we have written 56 as a product of prime numbers. This is called prime factorization of 56. The individual factors are called prime factors. For example, the prime factors of 56 are 2 and 7. Every number greater than 1 has a prime factorization. The idea is the same. Keep breaking the composite numbers into factors till only primes are left. The number 1 does not have any prime factorization. it is not divisible by any prime number. What is the prime factorization of a prime number like 7? It is just 7. We cannot break it down any further. Let us see a few more examples. By going through different ways of breaking down the number, we wrote 63 as 3 into 3 into 7 and as 3 into 7 into 3. Are they different? Not really. The same prime numbers 3 and 7 occur in both cases. Further, 3 appears 2 times in both and 7 appears once. Here you can see 4 different ways to get prime factorization of 36. Observe that in all 4 cases we get 2 2's and 2 3's. The prime factorization of 36 in 4 different ways is shown in a picture here. Multiply back to see that you get 36 in all 4 cases. For any number, it is a remarkable fact that there is only one prime factorization, except that the prime factors may come in different orders. Page number 119. As we explained here, the order is not important. However, as we saw in these examples, there are many ways to arrive at the prime factorization. Does the order matter? Here we are given a picture which displays the arrangement of the length as 5 units, breadth as 3 units, and its height as 2 units. Using this diagram, can you explain why 30 is equal to 2 into 3 into 5? No matter which way you multiply 2, 3 and 5. When multiplying numbers, we can do so in any order. The end result is the same. That is why when 2 2's and 2 3's are multiplied in any order, we get 36. In the later class, we shall study this under the names of commutativity and associativity of multiplication. Thus, the order does not matter. Usually, we write the prime numbers in increasing order. For example, 225 is equal to 3 into 3 into 5 into 5, or 30 is equal to 2 into 3 into 5. Prime factorization of a product of two numbers. When we find the prime factorization of a number, we first write it as a product of two factors. For example, 72 is equal to 12 into 6. Then we find the prime factorization of each of the factors. In the given example, 12 is equal to 2 into 2 into 3 and 6 is equal to 2 into 3. Now, can you say what the prime factorization of 72 is? The prime factorization of the original number is obtained by putting these together. 72 is equal to 2 into 2 into 3 into 2 into 3. Page number 120. We can also write this as 2 into 2 into 2 into 3 into 3. Multiply and check that you get 72 back. Observe how many times each prime factor occurs in the factorization of 72. Compare it with how many times it occurs in the factorizations of 12 and 6 put together. Figure it out. Question number 1. Find the prime factorizations of the following numbers: 64, 104, 105, 243, 320, 141, 1728, 729, 1024, 1331, 1000. Question number 2. The prime factorization of a number has 1 2, 2 3s and 1 11. What is the number? Question number 3. Find 3 prime factors all less than 30 whose product is 1955. Question number 4. Find the prime factorization of these numbers without multiplying first. A. 56 into 25. B. 108 into 75. C. 1000 into 81. Question number 5. What is the smallest number whose prime factorization has? Part A. 3 different prime numbers. Part B. 4 different prime numbers. Prime factorization is of fundamental importance in the study of numbers. Let us discuss 2 ways in which it can be useful. Using prime factorization to check if 2 numbers are co-prime. Let us again take the numbers 56 and 63. How can we check if they are co-prime? We can use the prime factorization of both numbers. 56 is equal to 2 into 2 into 2 into 7 and 63 is equal to 3 into 3 into 7. Now, we see that 7 is a prime factor of 56 as well as 63. Therefore, 56 and 63 are not co-prime. What about 80 and 63? Their prime factorizations are given here as 80 is equal to 2 into 2 into 2 into 2 into 5 and 63 is equal to 3 into 3 into 7. There are no common prime factors. Can we conclude that they are co-prime? Suppose they have a common factor that is composite. Would the prime factors of this composite common factor appear in the prime factorization of 80 and 63? Page number 121. Therefore, we can say that if there are no common prime factors, then the 2 numbers are co-prime. Let us find some more examples. Example, consider 40 and 231. Their prime factorizations are as under. 40 is equal to 2 into 2 into 2 into 5 and 231 is equal to 3 into 7 into 11. We see that there are no common primes that divide both 40 and 231. Indeed, the prime factors of 40 are 2 and 5, while the prime factors of 231 are 3, 7 and 11. Therefore, 40 and 231 are co-prime. Example, consider 242 and 195. Their prime factorizations are as follows. 242 is equal to 2 into 11 into 11 and 195 is equal to 3 into 5 into 13. The prime factors of 242 are 2 and 11. The prime factors of 195 are 3, 5 and 13. There are no common prime factors. Therefore, 242 and 195 are co-prime. Using prime factorization to check if one number is divisible by another. We can say that if one number is divisible by another, the prime factorization of the second number is included in the prime factorization of the first number. We say that 48 is divisible by 12 because when we divide 48 by 12, the remainder is 0. How can we check if one number is divisible by another without carrying out long division? Example, is 168 divisible by 12? Find the prime factorizations of both. 168 is equal to 2 into 2 into 2 into 3 into 7 and 12 is equal to 2 into 2 into 3. Since we can multiply in any order, now it is clear that 168 is equal to 2 into 2 into 3 into 2 into 7. That is equal to 12 into 14. Therefore, 168 is divisible by 12. Another example, is 75 divisible by 21? Find the prime factorizations of both. 75 is equal to 3 into 5 into 5 and 21 is equal to 3 into 7. Page number 122. As we saw in the discussion here, if 75 was a multiple of 21, then all prime factors of 21 would also be prime factors of 75. However, 7 is a prime factor of 21, but not a prime factor of 75. Therefore, 75 is not divisible by 21. Example, is 42 divisible by 12? Find the prime factorizations of both. 42 is equal to 2 into 3 into 7 and 12 is equal to 2 into 2 into 3. All prime factors of 12 are also prime factors of 42. But the prime factorization of 12 is not included in the prime factorization of 42. This is because 2 occurs twice in the prime factorization of 12 but only once in the prime factorization of 42. This means that 42 is not divisible by 12. We can say that if one number is divisible by another, then the prime factorization of the second number is included in the prime factorization of the first number. Figure it out. Question number 1. Are the given pairs of numbers co-prime? Guess first and then use prime factorization to verify your answer. Part A, 30 and 45. Part B, 57 and 85. Part C, 121 and 1331. Part D, 343 and 216. Question number 2. Is the first number divisible by the second? Use prime factorization. Part A, 225 and 27. Part B, 96 and 24. Part C, 343 and 17. Part D, 999 and 99. Question number 3. The first number has prime factorization 2 into 3 into 7 and the second number has prime factorization 3 into 7 into 11. Are they co-prime? Does one of them divide the other? Question number 4. Guna says any two prime numbers are co-prime. Is he right? 5.5 divisibility tests. So far, we have been finding factors of numbers in different contexts, including to determine if a number is prime or not, or if a given pair of numbers is co-prime or not. Page number 123. It is easy to find factors of small numbers. How do you find factors of a large number? Let us take 8560. Does it have any factors from 2 to 10? 2, 3, 4, 5, etc., 9, 10? It is easy to check if some of these numbers are factors or not without doing long division. Can you find them? Divisibility by 10. Let us take 10. Is 8560 divisible by 10? This is another way of asking if 10 is a factor of 8560. For this, we can look at the pattern in the multiples of 10. The first few multiples of 10 are 10, 20, 30, 40 and so on. Continue this sequence and observe the pattern. Is 125 a multiple of 10? Will this number appear in the previous sequence? Why or why not? Can you now answer if 8560 is divisible by 10? Consider this statement. Numbers that are divisible by 10 are those that end with 0. Do you agree? Divisibility by 5. The number 5 is another number whose divisibility can easily be checked. How do we do it? Explore by listing down the multiples 5, 10, 15, 20, 25 and so on. What do you observe about these numbers? Do you see a pattern in the last digit? What is the largest number less than 399 that is divisible by 5? Is 8560 divisible by 5? Consider the statement. Numbers that are divisible by 5 are those that end with either a 0 or a 5. Do you agree? Divisibility by 2. The first few examples of 2 are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 and so on. What do you observe? Do you see a pattern in the last digit? Page number 124. Is 682 divisible by 2? Can we answer this without doing the long division? Is 8560 divisible by 2? Why or why not? Consider this statement. Numbers that are divisible by 2 are those that end with 0, 2, 4, 6 or 8. Do you agree? What are all the multiples of 2 between 399 and 411? Divisibility by 4. Checking if a number is divisible by 4 can also be done easily. Look at its multiples. 4, 8, 12, 16, 20, 24, 28, 32 and so on. Are you able to observe any patterns that can be used? The multiples of 10, 5 and 2 have a pattern in their last digits, which we are able to use to check for divisibility. Similarly, can we check if a number is divisible by 4 by looking at the last digit? It does not work. Look at 12 and 22. They have the same last digit, but 12 is a multiple of 4 while 22 is not. Similarly, 14 and 24 have the same last digit, but 14 is not a multiple of 4 while 24 is. Similarly, 16 and 26 or 18 and 28. What this means is that by looking at the last digit, we cannot tell whether number is a multiple of 4? Can we answer the question by looking at more digits? Make a list of multiples of 4 between 1 and 200 and search for a pattern. Find numbers between 330 and 340 that are divisible by 4. Also, find numbers between 1730 and 1740 and 2030 and 2040 that are divisible by 4. What do you observe? Is 8536 divisible by 4? Consider these statements. First one, only the last two digits matter when deciding if a given number is divisible by 4. Second, if the number formed by the last two digits is divisible by 4, then the original number is divisible by 4. Third, if the original number is divisible by 4, then the number formed by the last two digits is divisible by 4. Do you agree? Why or why not? Page number 125. Divisibility by 8. Interestingly, even checking for divisibility by 8 can be simplified. Can the last two digits be used for this? Find numbers between 120 and 140 that are divisible by 8. Also, find numbers between 1120 and 1140 and 3120 and 3140 that are divisible by 8. What do you observe? Change the last two digits of 8560 so that the resulting number is a multiple of 8. Consider these statements. First, only the last three digits matter when deciding if a given number is divisible by 8. Second, if the number formed by the last three digits is divisible by 8, then the original number is divisible by 8. Third, if the original number is divisible by 8, then the number formed by the last three digits is divisible by 8. Do you agree? Why or why not? We have seen that long division is not always needed to check if a number is a factor or not. We have made use of certain observations to come up with simple methods for 10, 5, 2, 4, 8. Do we have such simple methods for other numbers as well? We will discuss simple methods to test divisibility by 3, 6, 7 and 9 in later classes. Figure it out. First, 2024 is a leap year, as February has 29 days. Leap year occurs in the years that are multiples of 4, except for those years that are evenly divisible by 100 but not 400. Part A. From the year you were born till now, which years were leap years? Part B. From the year 2024 till 2099, how many leap years are there? Question number 2. Find the largest and the smallest 4-digit numbers that are divisible by 4 and are also palindromes. Question number 3. Explore and find out if each statement is always true, sometimes true or never true. You can give examples to support your reasoning. Page number 126. Part A. Sum of two even numbers gives a multiple of 4. Part B. Sum of two odd numbers gives a multiple of 4. Question number 4. Find the remainders obtained when each of the following numbers are divided by Part A 10, Part B 5, Part C 2. The numbers are 78, 99, 173, 572, 980, 1111, 2345. Question number 5. The teacher asked if 14,560 is divisible by all of 2, 4, 5, 8 and 10. Guna checked for divisibility of 14,560 by only two of these numbers and then declared that it was also divisible by all of them. What could those two numbers be? Question number 6. Which of the following numbers are divisible by all of 2, 4, 5, 8 and 10? 572, 2352, 5600, 6000 and 77622,160. Question number 7. Write two numbers whose product is 10,000. The two numbers should not have 0 as the units digit. 5.6. Fun with numbers. Special numbers. There are 4 numbers in the given box. Which number looks special to you? Why do you say so? We have 4 numbers written in a box as 9, 16, 25, 43. Look at what Guna's classmates have to share. Karnavati says 9 is special because it is a single digit number, whereas all the other numbers are 2-digit numbers. Gurupreet says 9 is special because it is the only number that is a multiple of 3. Murugan says 16 is special because it is the only even number and also the only multiple of 4. Gopika says 25 is special as it is the only multiple of 5. Yadnaiki says 43 is special because it is the only prime number. Radha says 43 is special because it is the only number that is not a square. Page number 127. Here are some boxes with 4 numbers in each box. Within each box, try to say how each number is special compared to the rest. Share with your classmates and find out who else gave the same reasons as you did. Did anyone give different reasons that may not have occurred to you? Here we have 4 boxes. In the first box, the 4 numbers written are 5, 7, 12, 35. In the second box, we have numbers 3, 8, 11, 24. In the third box, we have numbers 27, 3, 123, 31. In the fourth box, we have 17, 27, 44 and 65. A prime puzzle. The figure on the left gives the puzzle. The figure on the right gives the solution of the puzzle. Think what the rules can be to solve the puzzle. On the left, we have 9 blank boxes And in the horizontal row given below, we have 170, 30 and 63. And in the rows, along with the 3 rows, we have the numbers 75, 42 and 102. In the solution puzzles, the numbers written are 5, 5, 3, 75, 2, 3, 7, 42, 17, 2, 3, 102. And in each column, we have the numbers below as 170, 30 and 63. Rules: fill the grid with prime numbers only so that the product of each row is the number to the right of the row and the product of each column is the number below the column. We have two pictures here in which we have 9 boxes and the numbers written against them are 105, 20, 30. And below the columns, the numbers written are 28, 125, 18. In the next picture, again we have 9 squares blank and the numbers written in the rows are 8, 105, 70. And the numbers written below each column are 30, 70, 28. Page number 128. Here also we have two pictures in which we have 9 blank boxes and the numbers written in the rows against them are 63, 27, 190. And the numbers written below each column are 45, 42, 171. In the next picture, again we have 9 boxes and the numbers written along the rows are 343, 660, 44. And the numbers written below each column are 28, 154, 231. Summary: if a number is divisible by another, the second number is called a factor of the first. For example, 4 is a factor of 12 because 12 is divisible by 4. Within brackets, 12 divided by 4 is equal to 3. Prime numbers are numbers like 2, 3, 5, 7, 11, etc. that have only two factors, namely 1 and themselves. Composite numbers are numbers like 4, 6, 8, 9, etc. that have more than two factors. That is, at least one factor other than 1 and themselves. For example, 8 has a factor 4 and 9 has the factor 3, so 8 and 9 are both composite. Every number greater than 1 can be written as a product of prime numbers. This is called the numbers prime factorization. For example, 84 is equal to 2 into 2 into 3 into 7. There is only one way to factorize a number into primes, except for the ordering of the factors. Two numbers that do not have a common factor other than 1 are called to be coprime. To check if two numbers are coprime, we can first find their prime factorizations and check if there is a common prime factor. If there is no common prime factor, they are coprime and otherwise they are not. A number is a factor of another number if the prime factorization of the first number is included in the prime factorization of the second number. This is the end of chapter 5.
Ganit Prakash. You were just listening to this audiobook, Textbook of Mathematics for Grade 6. Narration Swarnlata. Academic Coordinator Dr. Prakash Vadigar. Technical Coordination Bati Langlingdo. Sound Recordist Vikas Sangwan and Virendra Rawat. Assistance in Production Chetana Sharma. Directed and produced by Vimlesh Chaudhary. This audiobook is presented to you by CIET NCERT, New Delhi, India.